Ask any architect what makes a project succeed, and you will hear about design intent. Ask any owner the same question, and you will hear about whether the air conditioning works in August. Building systems, structural, mechanical, electrical, plumbing, and envelope carry roughly 2/3 of construction cost and almost all of the operating costs the owner lives with for the next 40 years. Picking them well is the difference between a building that performs and one that becomes a chronic complaint. On the exam, any wrong reading of the trade-offs costs you the question. Here are 4 reasons this module carries the weight the PPD exam gives it. 4 reasons system selection carries this much exam real estate. First, foundations are the silent expense. The choice between spread footings, mat foundations, and deep piles is dictated by soil bearing capacity, water table, and load. And the wrong call doesn't just cost more, it cascades into structural redesign that the schematic budget never planned for. Second, HVAC is climate-driven and load-driven, and the exam reads location and program before it reads anything else. A VAV system makes sense in one climate, a radiant slab makes sense in another, a heat pump fits a third. Pick wrong, and you commit the building to inefficiency for 40 years. Third, plumbing supply, waste, and vent sizing, plus wall assembly U values interlock with ASHRAE 90.1 and the IECC Energy Code. The system's decisions and the Energy Code compliance path live in the same document. And fourth, LEED is a credit clustering game. Some credits stack. Daylighting earns you both energy and indoor environmental quality points, and some compete. The exam tests whether you see the clusters. Here are the 6 subsections in the order the module walks them. Walking the 6 subsections. 2.1 defines the architect's role in systems selection, coordinator across engineering disciplines, not designer of the systems themselves. 2.2 covers shallow foundation systems, spread footings, strip footings, and mat foundations, and the soil conditions that make each one the right call. 2.3 is an overview of HVAC system types, VAV, fan coil, VRF, radiant, and the rest, with the climate and program logic that selects between them. 2.4 is plumbing, supply pressure, waste and vent sizing, water heating, and the codes that govern each. 2.5 walks wall assembly types from solid masonry to cavity walls to rain screen systems, with the thermal and moisture behavior of each. And 2.6 maps LEED V4 credit structure, the 5 major categories, the prerequisites, and how credits cluster around integrated design. One posture shift before we step into section 2.1. 4 things to hold in mind. First, every system selection is a 40-year commitment for the owner, not a schematic design line item. The exam writes its questions from the owner's service life lens. The right answer is the one that performs over time, not the one that's cheapest at bid. Second, climate and program drive system choice more than designer preference. When the prompt gives you a hot, humid climate and a hospital program, the answer set narrows dramatically before you even read the options. Third, the building envelope, the HVAC system, and the energy code are one interlocking question. You cannot pick a wall assembly without knowing the mechanical load it serves, and you cannot pick a mechanical system without knowing the envelope feeding it. And fourth, LEED rewards integration. Credits that share a design move cluster, credits that fight each other compete, and the exam tests whether you see which is which. With that posture set, we step into section 2.1. Picture this scene from a real architecture firm. A construction administrator is on the phone with the contractor, and the contractor is yelling. The HVAC system was undersized for the occupancy, and the structural system couldn't accommodate the ductwork. 2 systems, both wrong, and the architect's drawings were the place those decisions came together. Building systems are not a technical box you check before issuing for construction. They are the organs of the building. Pick the wrong structural system, and the building can't resist its lateral loads. Pick the wrong mechanical system, and the indoor air quality degrades until people get sick. The architect who treats system selection as a delegation to engineers is the architect who gets named in the lawsuit when the design fails to perform. Let me show you exactly how each system failure maps to a specific harm the public absorbs. 5 failure modes, and the harm each one produces is concrete enough that you could line up the consequence with a newspaper headline. A structural system that can't resist lateral loads doesn't just creak. The building collapses or suffers major damage in a seismic or wind event, and the architect's stamp is on the drawings. A mechanical system that can't maintain ventilation rates allows indoor air quality to degrade until occupant complaints turn into health claims. An undersized fire suppression system lets a fire grow beyond what the sprinklers can hold, and occupants can't get out in time. Electrical without emergency power leaves egress lighting dark when the grid drops, and the exit signs go with it. And plumbing cross-connections contaminate potable water. A single bad backflow assembly can turn into a public health emergency. None of these are abstract risks. They are the specific reasons NCARB tests building systems. Each of those failure modes points to a different reason the exam treats system selection as life safety territory. 4 reasons this content lives on the exam and not in a single engineering elective. First, the architect is the integrator. Engineers design subsystems, but the architect is the one responsible for them working together as one functioning building. Second, selection failures are not paperwork problems. Collapse, fire, ventilation failure, and electrical failure each end in deaths the architect's drawings could have prevented. Third, the architect signs and seals the drawings, which means responsibility for the whole assembly does not stop at the discipline boundary. You are accountable for the structural engineer's work appearing in your construction documents. And fourth, the decisions you make in schematic design are nearly impossible to reverse later. By the time the structural grid is locked, the HVAC zones are sized, and the egress strategy is documented, changing the structural system means redrawing the project. The exam tests this because failing to grasp it puts the architect on the wrong end of an expert witness deposition. Walk away with these 5 anchors when you sit down to make a system selection. 5 takeaways to anchor this section. 5 building systems together define how the building performs over its full life: structural, mechanical, electrical, plumbing, and fire protection. Each system has a specific failure mode that maps to a specific harm the public absorbs, which is why NCARB treats selection as life safety content rather than technical elective material. The architect is the integrator. Your job is not to do every engineer's calculations, it is to make sure every engineer's piece works together as one building. Selection failures are direct life safety failures, not abstract performance issues, and the choices you make in schematic design are functionally permanent. Once the grid is locked and the zones are sized, you do not get to undo them without rewriting the project. Treat selection like the design decision it is. Every building has to resist forces, and the candidates who fail the exam on structural questions are the ones who think load types are interchangeable. There are 6 categories you have to keep straight, and each one behaves differently in the structural model. Dead loads are permanent: the self-weight of the structure, the floor finishes, the partitions that stay in place, and you calculate them from the actual material weights. Live loads are temporary and movable, like people, furniture, and stored boxes, but you do not calculate live loads. The IBC prescribes them by occupancy classification, which is why a candidate who guesses the live load instead of looking it up is making a coin flip bet on a question with one right answer. Get the load wrong on a real project, and the engineer who relied on your occupancy classification is personally liable when the floor deflects. Lateral loads, wind and seismic, act sideways and need entirely different resisting systems than the columns that carry gravity down. Here are the 6 load categories you need to keep distinct, with the examples the exam draws from. 6 categories, and the exam will mix them in a question to see whether you can sort them. Dead loads are permanent self-weight, structure, finishes, roofing, the MEP equipment that's bolted in. Live loads are temporary and movable, which means people, furniture, and stored material. The values come from code, not from a takeoff. Wind is a lateral load that acts on the building's surfaces, positive pressure on the windward face, negative or suction pressure on the leeward face. Seismic is also lateral, but it comes from the ground accelerating under the building. The force is proportional to the mass of the structure, which is why heavier buildings draw bigger seismic loads even with the same ground motion. Snow is a gravity load that piles up on the roof, adjusted for exposure, thermal conditions, and slope. And rain is a gravity load that matters most on flat roofs with internal drains or scuppers. A clogged drain can pond the roof until it fails. Live load values are where careless candidates lose easy points. Memorize these 8. 8 live load values come up often enough to memorize, and the exam writers know which pairs trip candidates up. Residential private rooms come in at 40 pounds per square foot, the lowest of the common occupancies. Office is 50, which sounds intuitive until you realize the corridor in that same office building above the first floor is 80, not 50. Assembly with fixed seats fastened to the floor is 60. Assembly with movable seats jumps to 100 because chairs move and crowds shift their weight. First floor retail is also 100. Light storage is 125 and heavy storage is 250. Neither one in this table, but worth memorizing for the warehouse and big box questions. The trap the exam plants is the corridor and the first floor retail. Both are 100 PSF or higher. Both serve high traffic public space, and a candidate who answers 50 because the building is an office misses the point of the question. 2 of these values almost always appear in exam questions designed to catch the careless. Watch for them. 4 live load traps that show up over and over on the exam, and each one rewards candidates who memorize the table instead of guessing from intuition. The first is corridors above the first floor. They are 80 pounds per square foot, not the 50 of the office space they connect, because a corridor concentrates traffic that the office floor does not. The second is assembly with movable seats, 100 pounds per square foot, almost double the 60 of fixed seat assembly, because movable seats let crowds shift their weight and create temporary point loads. The third is first floor retail, also 100 pounds per square foot, much higher than the second floor office above it, because retail floors carry merchandise displays and concentrated foot traffic. And the fourth is heavy storage at 250 pounds per square foot, the highest common live load you'll see on the exam, and a value that makes warehouse and big box structural design fundamentally different from office construction. Carry away the load type distinctions and these specific live load values. 5 takeaways from this section. There are 6 load categories: dead, live, wind, seismic, snow, and rain. And each one behaves differently enough that mixing them up costs structural points. Dead loads are calculated from the actual material weights of the assembly. Live loads are prescribed by the IBC based on occupancy classification, and you look them up rather than guess them. Wind and seismic are lateral loads that act sideways and require dedicated lateral force resisting systems, shear walls, braced frames, or moment frames, separate from the columns that carry gravity. Corridors above the first floor are 80 pounds per square foot, regardless of the occupancy they serve, a common exam trap that catches candidates who answer the office number. And movable seat assembly, along with first floor retail, are both 100 PSF, both higher than candidates expect, and both worth committing to memory before you sit for this exam. The load path is the route forces take through the structure from the point where they arrive to the soil under the foundation. The single thing every architect needs to know about the load path is that it has to be continuous. If any link is missing, undersized, or improperly connected, the structure fails at that point. When a load path break causes a partial collapse in a real building, the architect of record is the first person named in the lawsuit, because the drawings are the document that says the path exists. The exam tests this idea in a specific way. It shows you a partial structural layout and asks you to identify where the load path is broken, or which element is doing work that nothing was sized for. Candidates who fail the exam on these questions are usually the ones who can recite that beams sit on columns, but can't tell you what carries the load when a column ends in the middle of a floor with no transfer girder beneath it. Continuous means continuous. Every floor down to the foundation, with no orphaned elements transferring load they cannot deliver. Gravity loads follow a 6-step path, top to bottom. Let me walk you through it. 6 steps for gravity loads, top to bottom. The roof or floor surface receives the load first. Dead weight of the assembly, live load from occupants and furniture, snow or rain depending on the level. Decking or sheathing, plywood, metal deck, or concrete topping, transfers that surface load down to the joists or purlins. The joists or purlins, in turn, transfer the load to whatever beam or girder they span between. The beams and girders then deliver the accumulated load to either columns or bearing walls. Columns and walls drop the load all the way down to the foundation, picking up the loads of every floor they pass through. And the foundation spreads it into the soil through bearing pressure on a footing or friction along a pile. Every one of those 6 links has to be sized for everything above it. If a beam is undersized at step 4, every load that was supposed to reach the column at step 5 fails to arrive, and the system collapses somewhere between the two. Lateral loads follow a different path. Diaphragms collect them, and shear walls or frames resist them. Lateral loads follow a parallel but different path, and the exam likes to test whether you can keep the 2 paths separate. Wind pressure on the building surfaces, or seismic acceleration from the ground, applies a lateral force first. Wind pushes against the windward face. Seismic rocks the whole mass sideways. The floor or roof diaphragm, usually the concrete slab or the metal deck with topping, collects that lateral force across the entire floor plate, acting like a deep horizontal beam. The diaphragm then transfers the collected force to the vertical resisting elements located at the perimeter or core. Those vertical elements, shear walls, braced frames, or moment frames, resist the lateral load by developing tension and compression in their members. The vertical elements deliver the lateral force down to the foundation, often with much larger uplift demands at the windward edge than gravity alone would create. And the foundation has to resolve the force through bearing, friction, and uplift restraint, which is why lateral resisting foundations are often deeper and heavier than gravity foundations would be by themselves. Carry the continuity rule and these 2 paths into every structural question on the exam. 5 takeaways from this section. The load path must be continuous from the point of application to the soil. One break anywhere in the chain is a structural failure waiting to happen, which is exactly what the exam tests when it shows you an incomplete structural diagram. Gravity loads follow 6 steps top to bottom: surface, decking, joists or purlins, beams or girders, columns or walls, foundation, and into the soil. Lateral loads follow a parallel 6-step path: applied force, diaphragm collection, transfer to vertical elements, shear walls or frames resisting in tension and compression, drop to foundation, and resolution into soil. Diaphragms function as deep horizontal beams that distribute lateral force across the floor plate to the vertical resisting elements. And foundations for lateral loads must resist uplift in addition to gravity bearing, which is why lateral loaded foundations are often deeper and heavier than the gravity case alone would require. Choosing a structural system is the single decision that determines whether your floor plan actually works. And architects who pick the wrong system fail the exam questions written around this content. Bearing wall systems are cheap and simple, but they cap your spans at about 25 feet and they force your openings to line up vertically, which means the column grid choice on level 1 decides what your tenant fit-outs can look like for the next 60 years. Frame systems let you have open floor plans and big spans, but you pay for them in steel tonnage and connection complexity. And long span systems open up arenas, airports, and convention floors, but they demand attention to lateral bracing and connection detailing that bearing walls do not. The architect who picks a structural system without understanding what each one trades away is the architect whose schematic design has to be rebuilt in design development. And that rework reads as fee absorbed by the firm. 5 primary system types cover most projects. Match the system to the program before you draw the grid. 5 primary structural systems, each one paired with the program type it fits best. Bearing wall systems carry gravity through the walls themselves, which means openings are limited and floor plans repeat. They work for residential, low-rise, and any project where the layout repeats floor to floor with spans capped at about 25 feet. Post and beam separates the gravity load path from the enclosure. Columns and beams form the frame, and the walls become non-structural infill. That gives you flexible commercial floor plans at spans of 20 to 40 feet. Rigid frames use moment connections between beams and columns to resist both gravity and lateral loads at the same joints. They work for mid-rise buildings in seismic zones where open plans are required. Braced frames use diagonal members to resist lateral loads while gravity goes through separate columns and beams. They show up in industrial buildings and as the lateral system in high-rise cores. And long-span systems open up arenas, airports, and convention spaces with spans from 60 feet up past 300, at a cost in detailing complexity that the other 4 systems don't carry. Long-span systems are their own decision tree, and 6 types cover most of what the exam tests. 6 long-span systems cover the bulk of what the exam will test. Steel trusses span 60 to 150 feet and work because triangulated members are efficient in both tension and compression. Open web steel joists span 30 to 96 feet and have one feature the exam loves. MEP services can pass through the open web without coordination conflicts. Glulam beams, engineered wood, span 20 to 100 feet and offer exposed warmth that steel and concrete cannot match aesthetically. Space frames are 3-dimensional trusses that span 60 to 200 feet and distribute loads in multiple directions at once, which makes them useful for irregular roof shapes. Cable-stayed systems span 100 up past 300 feet by hanging the deck or roof from cables that work entirely in tension. And shell systems, thin, curved surfaces, span 100 to 300 feet by acting as structure and enclosure simultaneously, which is why famous shell roofs like the Sydney Opera House show their structure as their architecture. Carry these comparisons into the next section, where the same span ranges show up paired with material choices. 5 takeaways from the structural system types. There are 5 primary systems to know: bearing wall, post and beam, rigid frame, braced frame, and long span. Bearing wall systems cap spans at around 25 feet and require openings to repeat vertically, which limits floor plan flexibility but keeps the construction costs low. Frame systems, post and beam, rigid, and braced, give you open floor plans and longer spans, but they cost more in material and connections than bearing wall systems. Long span systems enable the column-free spaces that arenas and airports need, but they demand careful attention to lateral bracing and connection detailing that simpler systems do not. And the right move is to match the structural system to the program before you draw the column grid. Picking a system after the floor plan is locked is how you end up redesigning in design development. Architects who think structural material selection means picking one material and applying it everywhere are the same architects whose schematic budgets get blown up in design development and whose firms absorb the fee on the rework. The most common mid-rise commercial assembly in this country is a steel frame with concrete on metal deck floors and CMU shafts at the stair and elevator cores. 3 materials working together, because each one does something the other 2 cannot. Steel gives you span and speed of erection. Concrete gives you inherent fire resistance and mass for vibration control. CMU gives you the rated fire enclosure the building code requires at the shaft. Pick the wrong material for the fire-rated shaft, and the building fails plan review, which means the owner absorbs delays, and the architect of record is on the receiving end of the lawsuit. The competent move is to pick each material for what it does best, and design the connections between them. 4 primary materials cover almost every project. Here's how their properties compare. 4 materials, 6 properties that decide selection. Steel has the highest strength-to-weight ratio and excellent tension capacity, which is why it dominates long-span buildings. But unprotected steel loses about 50% of its yield strength at roughly 1100 degrees Fahrenheit, which is the temperature reached in a typical office fire within minutes. So steel buildings either get rated coating or get enclosed in concrete or gypsum. Concrete is excellent in compression and inherently fire-resistant because of its mass and low thermal conductivity. But it is poor in tension and needs reinforcing steel to handle any bending. Wood is good in tension parallel to the grain and renewable as a material, but combustible, which limits its use in tall buildings without special protection. And masonry is excellent in compression, excellent at fire resistance, but very poor in tension and capped at relatively short bearing wall spans. Each material lives where its strengths are doing useful work for the program. Match material to program. And remember, mass timber under IECC Type 4A now allows tall wood construction with proper protection. 4 scenarios that route you to the right material. Long span, fast schedule, and exposed framing, accepted as part of the architecture. That's steel. The strength-to-weight ratio enables the span. The prefabricated members let the erection schedule run weeks ahead of cast-in-place construction. And exposed steel can be the architectural expression if the fire rating is achieved through intumescent coating instead of enclosure. High occupant load combined with a fire-rated frame and vibration-sensitive floors. That's concrete. The inherent fire resistance handles the rating without separate fireproofing. The mass damps the vibration that thin steel floors can't, and the compressive strength matches the heavy loads. Low to mid-rise, where sustainability is driving the decision. Wood, and increasingly mass timber, because the embodied carbon stays low and the renewable supply means the material itself helps the project's environmental story. And bearing wall buildings with durable load-bearing facades. Masonry, because the service life is measured in centuries and the fire rating comes built in. Carry these 4 scenarios into the structural selection question on the exam. 5 takeaways from the structural materials section. Steel has the best strength-to-weight ratio of the 4 materials, but it loses about 50% of its yield strength near 1100 degrees Fahrenheit, and therefore needs fireproofing for any building required to maintain structure during a fire. Concrete provides inherent fire resistance and mass that damp vibration, and it is excellent in compression, but it is weak in tension and requires reinforcing steel to carry any bending loads. Wood is renewable and low in embodied carbon, but combustible in its standard forms. Mass timber under IECC Type 4A is changing the calculation for taller wood buildings when proper encapsulation is provided. Masonry is excellent at fire and compression, but very poor in tension, which is why masonry-bearing wall buildings cap at relatively short spans. And most real projects use a mix. Steel frame, concrete floors, CMU cores is the common mid-rise commercial assembly, because it picks the strength of each material for the role it plays. Shallow foundations are the first thing every architect should reach for when the soil report comes back, because they are the cheapest, the fastest, and the easiest to coordinate. The catch is that they only work when the soil within a few feet of grade can take the bearing pressure your columns are going to deliver. Push past that capacity, and you get differential settlement, cracked finishes, and the kind of soil-related lawsuit that depositions architects whose schematic design didn't account for the soils report on the very first day. There are 4 shallow types worth keeping straight, and they each solve a different problem. Get the type wrong, and a competent geotechnical engineer will catch it before you stamp the drawings. But the architect who never learned the difference is the architect who fails the exam question that asks which footing serves which condition. 4 shallow foundation types cover almost every cooperative soil site. Here they are. 4 shallow foundation types, each matched to a specific site condition. Spread footings are individual pads under each column, and they live 3 to 6 feet below grade. They are the right answer when the soil is competent at shallow depth and the columns are spaced far enough apart that their footings do not need to overlap. Strip footings are continuous, linear footings beneath bearing walls, 2 to 4 feet below grade, used in bearing wall buildings where the load is distributed along the wall rather than concentrated at columns. Combined footings serve 2 or more columns from a single pad, which is what you reach for when columns are too close to receive their own footings, or when a column is so close to the property line that an isolated footing would extend beyond the parcel. And mat foundations are a single, thick, reinforced slab beneath the entire building, 4 to 10 feet below grade. Used when soil bearing capacity is weak, column loads are heavy, water table is high, or you need to reduce differential settlement across an irregular plan. Differential settlement is the issue that ends up in court. Uneven movement cracks finishes and fails the exam question. 5 design considerations decide which type works for your site and your loads. 5 considerations that drive the design of every shallow foundation, and missing any one of them is how schematic drawings fail at structural review. Soil bearing capacity has to exceed the applied pressure your columns deliver. That is the first check, and it is the one most architects can recite. The footing has to extend below the frost depth in your climate zone because frost heave will lift any footing left in the freeze-thaw layer and crack the structure above it. Footing width is inversely proportional to soil bearing capacity, which means weak soil requires wide footings to spread the load over more square footage. Mat foundations exist precisely for the case where you need to spread the load over the entire footprint of the building, because the soil cannot tolerate concentrated loads. And settlement is the issue that often controls design more than capacity does. Total settlement might be fine across the building, but differential settlement of even a fraction of an inch between adjacent columns cracks walls and ends in claims against the architect of record. Carry these 4 types and 5 drivers into the deep foundation discussion, where the rules change. 5 takeaways for shallow foundations. There are 4 shallow types worth keeping straight: spread footings, strip footings, combined footings, and mat foundations. Spread footings sit under individual columns on competent soil and are the default when soil cooperates. Strip footings run continuously beneath bearing walls. Combined footings handle the property line case where 2 columns share 1 pad. Mat foundations are the answer when loads are heavy or soil is weak. They spread the load over the building footprint, reduce differential settlement, and resist hydrostatic uplift at high water tables. And the design driver that ends up causing the lawsuit is rarely raw bearing capacity. It is settlement, both total and differential, that cracks finishes and reaches the architect's professional liability policy. Deep foundations are what you reach for when the soil at the surface cannot do the job, which happens on coastal sites, on landfill, on liquefiable sands, and on any project where the geotechnical report tells you the bearing stratum is 20 feet below grade. The architect who treats deep foundations as the engineer's problem alone is the architect who finds out at building permit that the driven piles selected for an urban infill site cannot be installed without vibration cracking the neighbor's building, and the lawsuit follows. Deep foundations come in 2 families: driven piles, which the contractor hammers into the ground, and drilled shafts, which the contractor excavates and fills with concrete. Each family has subtypes worth knowing, and each subtype has site conditions that rule it out. Skip those distinctions and you fail the exam question that asks why driven piles are the wrong answer for a hospital expansion next to an existing tower. 5 deep foundation types cover almost every condition. Here are the ones the exam tests. 5 deep foundation types, each one matched to a specific set of conditions. Driven timber piles are the simplest and cheapest, wood poles hammered into the ground, and they serve light loads and temporary structures where capacity demands are modest. Driven steel H-piles are H-shaped steel sections driven down until they hit refusal in a hard-bearing stratum, and they handle heavy loads on sites where dense sand or bedrock is reachable. Driven precast concrete piles are used in marine environments where wood would rot and steel would corrode, and they carry moderate to heavy loads through friction and end bearing combined. Drilled shafts, sometimes called caissons, are drilled holes filled with reinforced concrete. They carry heavy loads, work well on variable soil, and produce almost no vibration, which makes them the standard for urban infill projects next to existing buildings. Micropiles are small diameter, drilled and grouted piles used where access is restricted, where existing foundations need underpinning, or where a retrofit cannot accommodate full-size piles. Pick the wrong type on a real project, and the contractor's installation claim becomes the architect's design defect lawsuit. Capacity comes from 3 mechanisms: end bearing, skin friction, or both in combination. 3 capacity mechanisms decide how a pile actually carries its load, and the exam tests whether you can match the mechanism to the soil profile. End-bearing piles transfer load down the pile shaft to a hard stratum at the tip, bedrock, dense sand, or hard clay deep below grade. The pile basically becomes a stiff column, delivering the load straight to competent material. Skin friction piles transfer load along the entire surface of the pile through friction with the surrounding soil. They work in cohesive clays and loose granular soils where there is no hard-bearing stratum to reach, and the capacity builds up over the full length of the pile. Combined behavior is what you see in most real-world conditions. Some end-bearing at the tip, plus some friction along the shaft, with the geotechnical engineer's calculation accounting for both. Knowing which mechanism a pile uses tells you what soil report parameters matter, what installation method makes sense, and which questions the exam writer is testing when the soil cross-section shows alternating soft and dense layers. Take these 5 types and 3 mechanisms into the foundation selection guide, where site conditions decide which one works. 5 takeaways for deep foundations. There are 5 deep foundation types worth memorizing: driven timber piles, driven steel H piles, driven precast concrete piles, drilled shafts or caissons, and micropiles. Driven piles cause vibration during installation, which becomes a real problem in urban areas where adjacent structures could be damaged. Drilled shafts are quieter, but generate spoils that have to be hauled off-site. Capacity comes from 3 mechanisms: end bearing at the pile tip, skin friction along the pile shaft, or both combined, with the geotechnical engineer's calculation handling the actual contribution of each. Drilled shafts are the default choice on urban infill sites precisely because driven pile vibration would crack neighboring buildings and end in a personally liable claim against the design team. And while the geotechnical report tells you which mechanism the soil supports, the site constraints, access, vibration limits, water table, neighboring structures, often decide which installation method is actually buildable. Foundation selection is not a personal preference. It is a calculation that starts with the geotechnical report and ends at the building code. The geotechnical engineer tells you what the soil can do. The IBC tells you where the footing has to go. The architect's job is to read both and pick the foundation type that matches the program, the loads, and the site constraints. Get this wrong, and the consequences arrive in 2 stages. First, the contractor flags it during construction and submits a change order that the owner refuses to pay. Second, when the building shows differential settlement 2 years in, the architect of record is personally liable for the design decision that the soils report should have warned them about. There is also a specific exam trap embedded in this section. Silt heaves worse than clay or sand under freezing conditions, and candidates who think frost heave is about cold alone fail the exam question that names the soil type explicitly. 6 site conditions cover the foundation selections the exam routinely tests. 6 site conditions, each with a specific foundation, answer the exam wants. Competent soil at the surface, with bearing capacity above 2,000 pounds per square foot, calls for spread footings. It is the simple, economical answer when soil cooperates. Weak surface soil with strong soil at depth is the textbook case for deep foundations, either driven piles or drilled caissons, because they punch through the weak layer to reach the bearing stratum. Uniformly weak soil with no good layer below it pushes you toward a matte foundation that spreads the load over the entire footprint, or friction piles that develop capacity along their full length. A high water table calls for a mat with waterproofing to resist hydrostatic uplift, which can otherwise float a light building right off its footing. Expansive clay sites need drilled shafts that extend past the active zone, where seasonal moisture causes shrinkage and swelling. Because shallow footings in expansive clay heave and settle with every season and crack the structure above. And sites adjacent to existing buildings call for drilled shafts specifically because of the vibration issue. Driven piles next to an old masonry tower cause the kind of damage that ends in a lawsuit. None of these are stylistic choices. Frost depth is the rule layered on top of every shallow foundation decision. 6 frost facts, and the exam tests every one of them. Frost depth is the depth at which ground freezes in winter, and it ranges from 0 in southern Florida to over 6 feet in the coldest parts of the country. Frost heave is the upward movement of soil that happens when water in the soil pores freezes and expands by about 9% of its volume, lifting whatever sits above it. Every footing must extend below the frost depth in its climate zone. Leave the footing in the freeze-thaw layer, and the heave cycle lifts and drops the structure every winter until the foundation cracks. 3 conditions are required for frost heave to actually occur: a freezing temperature reaching the soil, a frost-susceptible soil type that can wick water to the freezing front, and a water source available to feed that wicking. And here is the trap that catches the most candidates. Silt heaves worse than clay or sand, because silt has exactly the right combination of capillary action and permeability to draw water up to the freezing zone. Sands drain too fast, and clays are too tight. Finally, IBC Section 1809.4 requires every footing to be at least 12 inches below grade, even in a frost-free region. The absolute floor on footing depth applies whether or not your climate freezes. Carry the soil report logic and the silt and 12-inch rules into every foundation question. 5 takeaways for foundation selection. Foundation selection always starts with the soils report, which tells you what the soil can do, and ends with the building code, which tells you where the footing has to go. 6 site conditions map to 6 specific foundation answers: competent soil to spread footings, weak surface to deep foundations, uniformly weak soil to mat or friction piles, high water to a waterproofed mat, expansive clay to drilled shafts past the active zone, and adjacent existing buildings to drilled shafts to avoid vibration. Drilled shafts are the urban infill default precisely because driven pile vibration would damage neighbors and trigger the kind of claim the architect personally absorbs. Frost heave is worst in silt because silt has the right capillary behavior to draw water to the freezing front. Clay is too tight and sand drains too fast, which is the exam trap. And IBC Section 1809.4 sets the absolute floor on footing depth at 12 inches, even in frost-free regions, which means 12 inches is the minimum, even in Florida. Most architects treat HVAC selection as the mechanical engineer's job alone, and most architects pay for that decision the rest of the project. You do not pick a system by aesthetic preference. You pick it by the medium used to move heat in and out of occupied space, and that medium decides the ceiling depth, the chase locations, and the long-term operating cost of the building. The architect who lets the mechanical engineer pick the system without participating in the conversation ends up with a ceiling plenum that the ductwork does not fit into, and the construction change orders that follow are not cheap. They hit the architect's fee through omissions claims, and the firm absorbs the loss. There are 4 families based on delivery medium: all air, air-water, all-water, and refrigerant-based, and each family has a footprint on the architecture. All air systems need the most ceiling height because the ducts have to be large enough to move the conditioning load. All water systems need the least ceiling height, but require dedicated outdoor air ductwork on top of the hydronic piping. Refrigerant-based systems split the difference and serve well for retrofits where running new ductwork would tear apart finished spaces. Skip this classification and you fail the exam question that asks why a fan coil system was selected on a historic adaptive reuse. 4 categories cover almost every system the exam tests. 4 categories, each defined by what gets piped or ducted to the occupied space. All air systems move conditioned air through ductwork to every zone, and they win on humidity control and air quality filtration because the central air handler can scrub everything before it reaches the room. The cost is ceiling depth. Moving the entire thermal load on air requires large ducts. Air-water systems split the job. Air handles ventilation and a small fraction of the thermal load, while water carries most of the heating and cooling to terminal units like fan coils or chilled beams. The ductwork shrinks because the air is doing less work. All water systems push the trade-off further. Water carries essentially all the thermal load to hydronic terminal units, and ventilation arrives through a separate, dedicated outdoor air system. The ceiling space wins, but the building now has 2 distribution networks instead of 1. And refrigerant-based systems, the variable refrigerant flow family, pipe refrigerant directly from outdoor compressors to indoor units, which is why they have taken over the retrofit market. No chiller, no boiler, and only refrigerant lines to thread through existing walls. Inside those 4 categories live 6 common system types worth memorizing. 6 system types, each one matched to a program and a constraint. Packaged rooftop units are self-contained boxes sitting on the roof with ductwork dropping down, and they dominate small commercial work and single-zone retail because the install is fast and the equipment is cheap. Variable air volume systems are the workhorse of multi-zone office buildings. A central air handler conditions the air, and terminal boxes throttle the airflow to each zone based on the thermostat. Fan coil units put a small water coil and fan box in every room, which is exactly what hotels and hospitals need when each guest or patient controls their own temperature. Variable refrigerant flow systems pipe refrigerant from an outdoor compressor to individual indoor units, and they have taken over the mid-rise office retrofit market because no chiller plant means no mechanical penthouse. Radiant panels run hot or chilled water through tubes embedded in floors or ceilings, and they shine in high ceiling spaces and comfort-critical labs where air motion has to stay low. Ground source heat pumps exchange heat with the earth at a steady 55 degrees, and they deliver the highest efficiency available, provided the site can support the well field. Pick the wrong one, and the operating cost differential compounds for the building's life. Carry these 4 categories and 6 systems forward into the VAV versus CAV comparison. 5 takeaways for HVAC system selection. There are 4 categories based on the medium that delivers conditioning: all air, air-water, all-water, and refrigerant-based. And the category drives ceiling depth, chase locations, and operating cost more than any other early decision. All air systems give the best humidity control and the best central filtration, but they require the most sealing depth because all the thermal load travels on the air. All water systems give the least sealing depth because water carries the thermal load efficiently, but the trade-off is a second dedicated outdoor air system that adds its own ductwork and controls. Variable refrigerant flow systems have taken over the mid-rise office retrofit market precisely because they eliminate the chiller plant. Refrigerant lines fit into walls where new chilled water piping would not. And 6 common system types: packaged rooftop, variable air volume, fan coil, variable refrigerant flow, radiant panels, and ground source heat pumps map cleanly to specific program types and constraints, which is exactly how the exam tests the selection question. Ask any architect why variable air volume dominates commercial office design, and you will hear vague answers about efficiency. The real reason is one specific physics relationship, the fan affinity laws. Fan power varies with the cube of speed, which means cutting airflow to half of design drops fan energy to roughly 12% of full. Constant air volume systems cannot capture that savings because the fan runs at design speed whether the building is occupied or empty. But the trade-off is real, and the exam tests it directly. VAV costs more upfront for terminal boxes and controls. VAV struggles with humidity at low airflows, and VAV with reheat wastes energy by overcooling air centrally and reheating it at the terminal box. ASHRAE 90.1 limits reheat energy specifically because of this trade-off. The architect who specifies VAV on a laboratory because energy savings sounded good ends up personally liable when the fume hood pressurization fails and the contamination claim follows. 6 properties decide which system fits which program. 6 properties decide whether variable air volume or constant air volume is the right specification for a project. Airflow is the first split. VAV modulates flow zone by zone based on thermostat demand, while CAV holds airflow constant regardless of load. Energy use follows directly from that. VAV captures the cube law savings on the fan because fan power drops with the cube of speed, while CAV pays the full fan tariff every hour the system runs. Zone control favors VAV. Each terminal box has its own damper and its own thermostat, while CAV usually delivers a single thermostat for the whole air handling unit. First cost favors CAV. Fewer boxes, fewer dampers, simpler controls. Humidity control favors CAV. At design airflow, the central cooling coil always operates in its sweet spot, while VAV at low flow can let air pass too slowly to fully dehumidify. And the best fit application splits clean. VAV for multi-zone offices and schools where loads vary. CAV for laboratories, clean rooms, and pressurized spaces where airflow itself is the design parameter and cannot be allowed to drift. 6 components make up a typical VAV installation. 6 components every VAV installation needs. The air handling unit is the central machine: fan, heating coil, cooling coil, filter section, and outdoor air mixing box all packaged together, and its location drives the entire mechanical room layout. Supply ductwork carries conditioned air from the air handler out to every zone in the building, and ductwork sizing determines how much sealing depth the design needs to give back. VAV terminal boxes sit above the ceiling at each zone and modulate the airflow based on the zone thermostat. Boxes can be cooling only or include a reheat coil for zones that need warming on winter mornings. The return air system pulls air back to the air handler either through dedicated return ducts or through the ceiling plenum, and code rules on plenum-rated cabling apply if the return is unducted. Exhaust fans handle restrooms, kitchens, and any space where the building has to be kept negative relative to its neighbors. And the building automation system ties it all together, sequencing the components for comfort and for ASHRAE 90.1 compliance. Carry the cube law and the reheat penalty into the energy section that follows. 5 takeaways for the variable air volume versus constant air volume decision. The fan affinity laws say fan power varies with the cube of speed, which is why VAV captures large annual energy savings in any building where loads vary significantly through the day or week. Constant air volume wins on humidity control because the velocity of air across the central cooling coil stays at its design point, and dehumidification at the coil depends on that velocity. Constant air volume also wins on first cost because there are no terminal boxes, no individual dampers, and no zone-level controls to commission. VAV with reheat. The most common VAV configuration in commercial offices is regulated by ASHRAE 90.1, specifically because central cooling followed by zone reheating is the energy waste path that the code is trying to limit. And the right specification for laboratories and cleanrooms is constant air volume, because airflow in those spaces is not just a comfort variable, it is the parameter that maintains pressurization and contaminant control. Most architects treat ductwork selection as the mechanical engineer's problem alone, and most architects lose ceiling height that the design needed because they did. You compete directly with the mechanical system for every inch of ceiling space, and the duct type drives that competition more than any other choice. Rectangular sheet metal is the most flexible to fabricate, but takes the most ceiling depth. Round spiral sheet metal is more efficient on friction loss, but comes in fixed diameters. Flexible duct is cheap and installs fast, but a single kinked run can cut zone airflow in half. Ductboard has integrated insulation, but cannot be cleaned. On top of duct type, the zoning strategy decides where the boundaries fall. Perimeter zones need heating and cooling. Interior zones typically need cooling year-round, and every facade exposure deserves its own zone. Get zoning wrong, and tenants complain that one side of the floor is freezing while the other is overheating. The architect catches the call, and the comfort claim turns into a lawsuit when tenants leave and the owner sues the design team for lost rent. 4 duct types cover almost every project. Here is how they compare. 4 duct types, each with a clear strength and a clear weakness. Rectangular sheet metal, galvanized steel formed to custom dimensions, gives the maximum design flexibility and a cleanable interior, which makes it the standard for large commercial work. The cost is ceiling depth and labor. Round or spiral sheet metal has lower friction loss because the cross-section is naturally efficient, and the spiral lock seam means less leakage at fittings. The trade-off is fixed diameters. The duct does not bend to fit tight spaces the way rectangular ductwork can be reformed. Flexible duct, the wire-reinforced insulated tubing, is the cheapest and fastest to install, and it routes around obstructions easily. But it has very high friction loss when compressed or kinked, and code limits its run length to roughly 5 feet at the terminal connection. Past that, the airflow drops measurably. Ductboard, the fiberglass-faced product, comes with insulation already built in and fabricates fast. But it cannot be cleaned. The interior fibers erode over time, and it is unsuitable for any project where indoor air quality concerns drive the specification. Zoning matters as much as duct type. 6 considerations decide where the boundaries fall. 6 zoning considerations that shape the architectural ceiling plan as much as the mechanical drawings do. Perimeter zones are exposed to the weather and the sun. They need heating in winter when the wall loses heat to the outside, and they need cooling in summer when solar gain pushes the interior temperature up. Interior zones, the ones surrounded by other interior spaces, typically need cooling year-round because internal heat gains from people, lighting, and equipment exceed envelope losses even in January. Each facade exposure deserves its own zone. A south-facing tenant suite and a north-facing tenant suite cannot share a thermostat without one of them being uncomfortable for half the year. Special use spaces like server rooms with year-round high heat loads, kitchens with hood exhaust requirements, and conference rooms with sharp occupancy spikes all need dedicated systems sized to their specific load. The building automation system coordinates everything. sequences economizers, and stages equipment for partial load efficiency. And occupancy sensors plus carbon dioxide sensors enable demand-controlled ventilation, which reduces outdoor air when spaces are partially occupied and is required by ASHRAE 90.1 in many space types. Carry duct selection and zoning logic forward into the energy efficiency strategies. 5 takeaways for ductwork and zoning. There are 4 ductwork types in common use: rectangular sheet metal for flexibility, round or spiral sheet metal for low friction loss, flexible duct for cheap, fast routing, and duct board for integrated insulation. And each one trades first cost against performance and cleanability. Flexible duct length is capped by code at the terminal connection because friction loss rises sharply when the duct is compressed, bent, or routed past its useful run length. Perimeter zones need both heating and cooling because they are exposed to the weather, while interior zones almost always need cooling year-round because internal heat gains from people, lights, and equipment exceed envelope losses. Each facade exposure, north, south, east, and west, deserves its own zone because solar timing differs by facade, and a shared thermostat across exposures guarantees that someone is uncomfortable. And demand-controlled ventilation reduces outdoor air when spaces are partially occupied, using carbon dioxide and occupancy sensors to cut ventilation energy without compromising indoor air quality. ASHRAE 90.1 requires it in many space types. Most architects undervalue mechanical efficiency because the dollars show up on the owner's utility bill rather than the construction budget. You should care anyway. Mechanical conditioning typically accounts for roughly 40 to 60% of total commercial building energy use, which makes HVAC the single biggest lever for cutting operating cost. The architect whose owner returns 3 years later asking why utility bills are double the marketing brochure ends up explaining design decisions in front of a contractor and a consultant. And the architect's exposure includes a lawsuit alleging negligent misrepresentation if the energy model misled the owner. That is a personally liable exposure outside professional liability coverage. 6 strategies cover almost every credible energy reduction available. Airside economizers cut cooling energy when outdoor air is cool enough to handle the load. Energy recovery ventilators capture heat from exhaust air. Variable speed drives modulate fans and pumps down at partial load. Demand-controlled ventilation reduces outdoor air when spaces are partially occupied. High-efficiency equipment replaces baseline compressors and motors. And condensing boilers recover latent heat from flue gases instead of venting it. 6 efficiency strategies and their typical savings range. Here are the numbers the exam tests. 6 strategies and the energy savings each one delivers. Airside economizers cut 10 to 20% of cooling energy by using cool outdoor air directly when temperature and humidity allow. ASHRAE 90.1 requires economizers for most cooling systems above 54,000 BTU per hour in most climate zones. Energy recovery ventilators capture 15 to 30% of the ventilation load by transferring heat or moisture between the exhaust airstream leaving the building and the outdoor airstream coming in, which means the outdoor air arrives partly conditioned for free. Variable speed drives cut 20 to 50% of fan and pump energy by modulating motor speed at partial loads. This is the cube law strategy that makes VAV systems beat CAV on annual energy in the first place. Demand-controlled ventilation cuts 10 to 25% of ventilation energy by reducing outdoor airflow when occupancy sensors and carbon dioxide sensors indicate the space is partially used. High-efficiency equipment, premium efficiency motors, scroll compressors, brazed plate heat exchangers, adds 10 to 30% across the board. And condensing boilers recover 10 to 15% more energy than conventional boilers by condensing the water vapor in the flue gases and capturing the latent heat. 5 cube law facts every architect should commit to memory. 5 cube law facts every architect should know cold. First, Fan power varies with the cube of fan speed under the fan affinity laws, which is a fundamental physics relationship that applies to every centrifugal fan and pump in every mechanical system. Second, cutting fan speed by half drops fan power to roughly 12% of full design power, which is the most consequential single fact in mechanical energy use. Third, variable speed drives, sometimes called variable frequency drives, capture this cube law savings on every modulating fan and pump in the system, which is why retrofitting VSDs onto constant speed equipment is one of the highest return energy projects available. Fourth, ASHRAE 90.1 requires variable speed control on most large fan systems and most large pump systems, precisely because the cube law savings are too big to leave on the table. And fifth, the cube law is the underlying physics that makes variable air volume systems beat constant air volume systems on annual energy in any building where loads vary, because VAV lets the fan ride down the cube curve at partial load, while CAV keeps the fan at the top of the curve all the time. Carry these strategies forward to plumbing, electrical, and lighting, where similar code-driven efficiency rules apply. 5 takeaways for HVAC energy efficiency. Mechanical conditioning typically accounts for 40 to 60% of commercial building energy use, which means HVAC is the single biggest lever for cutting operating cost over the building's life. There are 6 strategies that cover almost every credible energy reduction: airside economizers, energy recovery ventilators, variable speed drives, demand-controlled ventilation, high-efficiency equipment, and condensing boilers, and most efficient buildings use several of them in combination. Airside economizers are required by ASHRAE 90.1 for most cooling systems above the threshold capacity in most climate zones, which means it is a code requirement rather than an optional upgrade. Fan power varies with the cube of speed, and variable speed drives capture that cube law savings on every modulating fan and pump, dropping fan energy to roughly 12% of full at half speed. And condensing boilers reach roughly 95% thermal efficiency by recovering latent heat from flue gases, compared to about 80% for conventional non-condensing boilers. Most architects treat plumbing as the engineer's responsibility alone, and you should not. Plumbing is the building system that fails most visibly when the design is wrong. A leak in the supply line shows up as water on the ceiling tile. A drain slope too shallow shows up as a clog the maintenance team cannot clear. And a vent stack missed in coordination shows up as sewer gas in the occupied space. The architect who skipped the plumbing coordination meeting is the architect whose tenant sues over the smell coming from the floor drain in the conference room. And the personal liability exposure for sewer gas in occupied space is not theoretical. There are 4 plumbing subsystems, and each one has a specific design constraint the exam tests. Domestic water supply needs minimum pressure at the highest fixture. Sanitary drainage needs slope and cleanouts and venting. The vent system has to reach open air or trap seals will siphon and let sewer gas escape. And storm drainage has to be sized to the rainfall intensity and kept separate from sanitary by code in almost every jurisdiction. Mix storm and sanitary together, and the wastewater treatment plant gets flooded during every rain event, and the design team gets the letter from the city. 4 subsystems, each with a distinct function and a distinct design driver. 4 plumbing subsystems, each with a specific function and a specific design issue the exam tests. Domestic water supply delivers hot and cold potable water to every fixture in the building, and the design issue is pressure. The code requires a minimum static pressure at the highest fixture, which drives the booster pump sizing on tall buildings and the pipe diameter throughout. Backflow prevention is the other piece, because contaminated water cannot be allowed to siphon backward into the potable supply. Sanitary drainage removes wastewater by gravity to the sewer or septic system, and the design issue is slope. The standard is 1/4 inch per foot, which is steep enough to keep solids moving, but not so steep that the liquid runs ahead of the solids and leaves a clog behind. Cleanouts are required at every change of direction. The vent system admits air into the drainage piping to prevent trap seals from siphoning when water flows past them. And the design issue is the connection to open air. Every vent has to reach the atmosphere either through the roof or through an air admittance valve where the code allows it. And storm drainage removes rainwater from the roof at a rate sized to the rainfall intensity for the project's climate, with strict separation from sanitary drainage required almost everywhere. 6 fixture unit facts decide how the pipes get sized. 6 fixture unit facts that decide how pipes get sized on every project. First, a fixture unit is a standardized measure of probable flow from a plumbing fixture, and it is the unit the IPC uses to size every line in the building. The number does not equal gallons per minute or anything else physical. It is a code table-driven number that represents probable use. Second, a water closet with a flush valve equals 4 fixture units, which is the highest single fixture load in most projects and dominates the sizing of restroom branch lines. Third, a lavatory equals 1 fixture unit and a bathtub equals 2, which gives a sense of the relative load on the system. Fourth, pipe sizing is based on total fixture units served, using code tables that map fixture unit count to pipe diameter for both supply and drainage. The tables are the document the engineer references for every project. Fifth, the diversity factor recognizes that not all fixtures operate simultaneously, which is why the pipe size for a 50 fixture restroom is much smaller than 50 times a single fixture line would suggest. And sixth, water supply sizing converts fixture units into gallons per minute through Hunter's curve or modified versions of it, and the result is the design flow that the pipe and booster pump have to support. Carry the 4 subsystems and the vent rule into the electrical and lighting section. 5 takeaways for plumbing system design. There are 4 plumbing subsystems: domestic water supply, sanitary drainage, the vent system, and storm drainage, and each one has a specific design issue keyed to a specific section of the IPC. Every trap must be vented, no exceptions. Without venting, water flowing past a trap creates suction that siphons the water seal out of the trap and lets sewer gas into the occupied space. Sanitary drainage slopes 1/4 inch per foot as the standard, which is steep enough to keep solids moving with the liquid, but not so steep that the liquid runs ahead and abandons the solids in the pipe. Storm drainage and sanitary drainage stay separate in almost every modern jurisdiction because combining them overloads the wastewater treatment plant during rain events and triggers regulatory enforcement. And pipe sizing uses the fixture unit method against IPC code tables, not a raw count of fixtures. Diversity factors recognize that not every fixture operates at the same instant, which is why a 50 fixture restroom needs a much smaller supply main than 50 single fixture lines would suggest. Most architects treat electrical distribution as the engineer's problem and stop thinking about it after schematic. You cannot afford that habit. The architectural decision is whether the program is sized correctly so the electrical room, the transformer pad, and the riser shafts land where they need to land. The architect who skipped the electrical coordination is the architect who finds out at design development that the 8-foot square electrical room shown on the schematic is supposed to fit a switchboard, a fire-rated bus duct riser, and code-required working clearance, and it does not. Which means the program loses square footage, the design fee absorbs the rework, and the firm gets sued by the owner for the schedule slip and the lost rent. Power steps down through 5 levels, from utility service at 4,160 volts to branch circuits at 120 or 208 volts at the outlet. Each step needs space, the right ventilation, and the right code-required clearances. On the lighting side, the design splits into 5 distinct functions: ambient illumination for general visibility, task lighting at work surfaces, accent lighting for visual interest, emergency lighting for code-required egress, and exit signage to mark the way out. Miss any of the 5 and the building fails plan review on a basic life safety requirement. 5 distribution levels move power from the street to the outlet. 5 levels of electrical distribution, each one stepping the voltage down for the next stage of use. Utility service is where the power arrives from the electric company, typically at medium voltage, between 4,160 and 13,800 volts, far too high for any building equipment to use directly. The transformer is the first step down, converting medium voltage to the 480 over 277 volt system that handles large commercial loads. The transformer needs ventilation, code-required clearance, and a pad outside or a vault inside, all of which the architect has to lay out early. The main switchboard is the central disconnect and the primary distribution panel for the building, sized to the total connected load. The room it sits in needs the working clearance required by the NEC and has to remain accessible to qualified electrical workers. Panel boards take the 480 supply and step it down through smaller transformers to 208 over 120 volts, the working voltage for receptacles and general lighting. And branch circuits run the final distance to outlets, fixtures, and equipment at 120 volts for general use and 208 or 277 for larger loads. Lighting design splits into 5 distinct functions worth memorizing. 5 lighting functions, each with a specific purpose and a specific code threshold the exam tests. Ambient or general lighting provides overall uniform illumination, with the target foot candle level pulled from the IES handbook for the specific space type. Roughly 30 foot candles for general office work, 50 for detailed work, and lower for circulation and lobby spaces. Task lighting provides focused, higher intensity illumination at the work surface, which lets the design lower the ambient level and save energy across the floor plate. Accent lighting highlights features and creates visual interest, typically running at 3 to 5 times the ambient level on the featured surface, so the contrast reads as deliberate. Emergency lighting is code required to illuminate the egress path during a power failure. The NEC requires 1 foot candle average at floor level along the egress route and 90-minute battery backup on every fixture in the system, which is what keeps the building safe when utility power drops. An exit signage marks the exit locations and points the direction of egress, illuminated and visible from every corridor and aisle. Miss either emergency lighting or exit signage, and the building fails plan review on a code-required life safety system with no possibility of a variance. Carry the 5 distribution levels and 5 lighting types into the lighting power density rules. 5 takeaways for electrical distribution and lighting. There are 5 distribution levels: utility service at medium voltage, transformer step down, main switchboard, panel board, and branch circuit, each one stepping voltage down for the next stage of use, and each one requiring space in the architectural plan. There are 5 lighting functions: ambient or general illumination, task lighting at work surfaces, accent lighting for visual interest, emergency lighting for egress, and exit signage to mark the way out. And the design has to provide all 5 to satisfy code and program. Emergency power is legally required for life safety loads including egress lighting, fire alarm, and fire pumps under NEC Article 700, which is the article every exam candidate should know by reference. Emergency generators must start within 10 seconds of power loss under the same article, which drives the type of generator and the type of transfer switch selected. And exit signs and egress lighting are non-negotiable code items. There is no variance available, no waiver, and no design exception that lets the architect skip either one. Most architects approve lighting layouts without ever running the wattage math. And most architects find out at permit review that you cannot do that anymore. Lighting power density, abbreviated LPD, is the number that controls whether the lighting design passes the energy code. The metric is watts per square foot of installed lighting power. and ASHRAE 90.1 caps it for every space type: open plan office, enclosed office, classroom, corridor, hospital patient room, parking garage. Every category has a number the design cannot exceed. The architect who lets the lighting designer specify decorative fixtures without checking the connected wattage gets the project redlined at permit. The owner pays the rework, and the firm gets sued for the schedule slip. And, on the exam, picking the wrong LPD method fails the question outright. Two methods are available for proving compliance. The building area method assigns a single LPD number to the whole building based on its primary function, which is simpler but less flexible. The space-by-space method assigns a different LPD limit to each space type and lets the design trade between spaces, which usually allows more total watts but requires careful tabulation. And do not confuse LPD with illuminance. LPD is the input wattage the fixtures draw, while illuminance in foot candles is the output light that reaches the work surface. Code limits the input. The IES handbook recommends the output. 6 representative LPD limits by space type. Numbers worth memorizing. 6 representative LPD limits worth memorizing for the exam. Open plan office space is capped at approximately 0.61 watts per square foot in the current edition of ASHRAE 90.1, a number low enough that LED fixtures are essentially required to comply because legacy fluorescent designs cannot make the cap. Enclosed office space allows approximately 1 watt per square foot, which gives the design some room because enclosed offices are smaller spaces where individual fixture choices have more variation. Classroom and lecture space allows approximately 1.2 watts per square foot, recognizing that educational spaces typically need higher illuminance for visual tasks like reading and writing. Corridors are capped at approximately 0.66 watts per square foot, which drives selection of efficient downlights or wall sconces and rules out decorative-only fixtures with high wattage. Retail general space allows approximately 1 watt per square foot for ambient lighting, with separate allowances available for accent and display lighting. And parking garages are capped at approximately 0.15 watts per square foot, the tightest commercial allowance, which has essentially forced the entire parking garage market to LED over the past decade. 5 efficiency strategies make hitting the LPD cap practical. 5 lighting efficiency strategies that make hitting the LPD cap practical on real projects. First, LED lighting delivers 80 to 150 plus lumens per watt, compared to roughly 15 for incandescent and 85 for legacy fluorescent. The efficacy difference is so large that LED is essentially the only path forward for any project chasing tight LPD allowances or pursuing LEED credits. Second, daylighting controls dim or switch off electric lights when natural daylight is sufficient, capturing the contribution of windows and skylights toward illuminance rather than running fixtures at full output regardless of daylight. Third, occupancy sensors turn off lights in unoccupied spaces, and they are required by ASHRAE 90.1 in many space types including offices, classrooms, conference rooms, break rooms, restrooms, and storage rooms. Fourth, task ambient lighting lowers the ambient level across the floor plate and provides focused task lights at workstations, which delivers the illuminance where it is needed without paying the wattage tariff for every square foot of ceiling. And fifth, high reflectance surfaces on walls and ceilings reduce the number of fixtures needed to hit a given illuminance, because the light bounces and contributes to the target foot candle reading. Carry the LPD framework and the efficiency strategies into the wall assembly section. 5 takeaways for lighting power density. LPD is watts per square foot of installed lighting power, and it is the metric that determines whether a lighting design passes the energy code check at permit submission. ASHRAE 90.1 caps LPD for every space type, with separate numbers for open office, enclosed office, classroom, corridor, retail, hospital patient room, parking garage, and dozens of other categories. Two compliance methods are available. The building area method assigns one LPD number to the whole building based on its primary function, while the space-by-space method assigns separate LPD limits to each space type and allows trading between them. LPD is the input wattage that the fixtures draw, not the output illuminance. Code limits the input, while the IES handbook recommends the output foot candle level for visual task performance. And LED lighting is essentially required to hit current LPD caps in most space types because the efficacy of LED at 80 to 150 plus lumens per watt is the only credible path to fitting useful illuminance into the wattage budget the code allows. Most architects pick a wall type because the cladding looks good in renderings, and you cannot afford to be that architect. Wall assemblies are ranked by how they manage water, and the moisture strategy decides whether the building leaks 5 years into occupancy or stays dry for its entire service life. The architect who picked cladding for aesthetics and not for moisture strategy is the architect whose firm gets the call about mold growth on the inside of the exterior wall, the architect personally liable in the lawsuit that follows, and the firm sued for the remediation cost on top of the rework. 4 wall types cover almost every building, and they range from worst to best on moisture reliability. Barrier walls rely on a single waterproof surface, which means any crack becomes a leak. Mass walls absorb moisture and slowly release it, which works in mild climates but fails in wet ones. Drainage walls with a cavity behind the cladding accept that some water gets through and provide a path for it to drain out, which is a fundamental advance over the barrier approach. And rain screen walls add pressure equalization on top of drainage, which eliminates the pressure differential that drives wind-driven rain through joints, the most reliable wall the industry knows how to build. 4 wall types ranked from least to most reliable on moisture management. 4 wall types, each one a different answer to the question of how the assembly manages water. Barrier walls, the face-sealed approach used in EIFS and single-wipe precast, rely on a single waterproof surface to keep water out. The reliability is the lowest of the 4 because any crack in the surface, any failed sealant joint, any installation defect becomes a direct path for water to enter the wall and become trapped behind the impermeable face. Mass walls, thick masonry, stone, log construction, absorb moisture during a wetting event, store it within the wall thickness, and slowly release it back to the atmosphere when conditions dry. They work in mild climates, where the drying cycle keeps pace with the wetting cycle, but they fail in wet climates where the wetting outpaces the drying and the wall stays saturated. Drainage walls, brick veneer over CMU backup with an airspace between, except that some water will get through the outer WIVE and provide a drained cavity for that water to escape through weep holes. The reliability climbs sharply because water no longer accumulates inside the wall. And rain screens add pressure equalization on top of drainage by venting the cavity to the outside, which eliminates the pressure differential that wind-driven rain needs to push water through joints, the most reliable wall available. 7 layers make up a properly designed wall assembly, from outside to inside. 7 layers make up a properly designed wall assembly, from outside to inside. The cladding sheds the majority of water that hits the wall in the first place. The drainage cavity behind the cladding lets infiltrated water drain down and out through weep holes. The water-resistive barrier behind the cavity provides backup waterproofing if water gets past the cladding. The insulation provides thermal resistance, and continuous insulation outboard of the framing avoids thermal bridging at studs. The air barrier controls air leakage across the entire enclosure and is sometimes combined with the water-resistive barrier in a single product. The vapor retarder controls moisture vapor diffusion and is placed on the warm side of insulation, with the warm side varying by climate zone. The interior finish completes the assembly with gypsum board or plaster. Miss any of the 7 layers, and the assembly fails one of its 3 jobs of keeping water, air, or vapor under control. Carry the 4 wall types and 7 layers into the roofing section that follows. 5 takeaways for wall assembly design. There are 4 wall assembly types ranked by moisture strategy. Barrier walls relying on a single waterproof surface. Mass walls absorbing and slowly releasing moisture. Drainage walls with a drained cavity behind the cladding. And rain screens adding pressure equalization on top of drainage. Barrier walls are the most failure-prone of the 4 because any crack in the waterproof surface, sealant joint, hairline crack in the cladding, installation defect, becomes a direct path for water to enter the assembly. Rain screens are the most reliable because pressure equalization eliminates the pressure differential that wind-driven rain needs to push water through joints, making the wall essentially self-protecting against driven rain. 7 layers make up a complete wall assembly from outside to inside: cladding, drainage cavity, water-resistive barrier, insulation, air barrier, vapor retarder, and interior finish. And missing any one of them compromises the assembly's performance. And continuous insulation outboard of the framing avoids the thermal bridging that steel studs would otherwise create, which is exactly why ASHRAE 90.1 mandates continuous insulation on most steel-framed walls in most climate zones. Most architects know the cladding palette better than the roofing palette. And most architects find out the hard way that you cannot specify a roof off the cladding intuition alone. Low-slope roofs and steep-slope roofs work by entirely different principles. Low-slope roofs, those under 3 and 12 pitch, rely on a continuous waterproof membrane because water does not shed quickly enough for overlapping pieces to work. Steep-slope roofs, those above 3 and 12, rely on gravity and the shingle principle. Overlapping pieces shed water down to the next overlap. Pick the wrong system for the pitch, and the building leaks on the first heavy rain. The owner sues the design team, the contractor blames the specification, and the architect, personally liable in the resulting lawsuit, cannot point to a code clause as cover because the code permits the membrane system selected. The roofing failure becomes a design defect claim. 6 low-slope systems handle almost every flat or near-flat roof. 6 low-slope roofing systems, each one a different answer to the membrane question. Built-up roofing layers, multiple plies of bitumen and reinforcing felt to create a redundant waterproof barrier, proven over decades, but hot to apply and slow to install. Modified bitumen is the next generation, supplying the bitumen in factory-made sheets with polymer modifiers like APP or SBS. Easier than built up, but the seams still demand torch application by skilled hands. Single-ply TPO membranes are heat-welded thermoplastic sheets that arrive white and reflective, perfect for cooling-dominated climates, with strong welded seams but a newer track record. Single-ply EPDM membranes are synthetic rubber sheets that have been around the longest of the single-ply family. Excellent flexibility, UV resistance, but adhesive seams that are weaker than welded. Single-ply PVC membranes weld like TPO and resist chemicals well, which is why they show up on hospital roofs and food processing plants. The downside is plasticizer migration over time and a higher first cost. And green roofs add a stormwater management layer, growing medium, and plants on top of a waterproof base. They help heat island and biodiversity, but they are heavy, expensive, and require maintenance the owner has to commit to. 5 steep slope materials carry the shingle principle. 5 steep slope materials and their service life ranges. Asphalt shingles work at 2 and 12 pitch with proper underlayment, and they last roughly 20 to 30 years before replacement, the cheapest and most common residential answer. Metal standing seam panels can go as low as 1/4 and 12 pitch because the standing seams themselves are watertight, and they last 40 to 60 years or more, which makes them attractive on commercial and institutional buildings where life cycle cost matters. Clay or concrete tile requires 2.5 and 12 minimum pitch and lasts 50 to 100 years or more, with the trade-off being the dead load on the structure, which has to be designed up front. Slate needs 4 in 12 minimum pitch and lasts the longest of any residential material, 75 to 200 years. But the material cost and the skilled labor make slate the premium option. And wood shingles or shakes need 3 in 12 minimum pitch and last 20 to 40 years, with fire treatment requirements that vary by jurisdiction and a maintenance regime the owner has to commit to. Match the material to the pitch and the climate, or the roof leaks early. Carry the low slope and steep slope split into the window performance section. 5 takeaways for roofing system design. Low slope roofs under 3 in 12 pitch rely on continuous membrane waterproofing because water does not shed quickly enough for overlapping pieces to work. The membrane is the only thing keeping water out. Steep slope roofs above 3 in 12 pitch rely on gravity and the shingle principle, where each overlapping piece sheds water down to the next overlap, and the underlayment serves only as a backup. 6 low-slope systems cover almost every flat or near-flat roof: built-up, modified bitumen, TPO, EPDM, PVC, and green roof, and each one trades first cost for durability and aesthetics. 5 steep slope materials range from 20-year asphalt shingles to 200-year slate, with metal standing seam, clay or concrete tile, and wood shakes filling in between. And matching the material to the pitch and the climate is non-negotiable. Pick wrong, and the roof leaks early. The owner sues, and the design team explains the specification in front of a judge. Most architects spec windows off manufacturer marketing literature, and you cannot do that anymore. The numbers in the marketing brochure are center of glass values measured on the glazing alone, and the certified NFRC label values for the whole assembly are always worse. The architect who specs to the marketing brochure and not to the NFRC label finds out at Energy Code Review that the whole window U factor missed the cap. The project gets redlined, the owner pays the substitution, the firm gets sued for the schedule slip, and the architect personally liable for the bad specification has to explain the difference in front of the licensing board. There are 5 NFRC-rated metrics that every window product carries: U factor for heat transfer, solar heat gain coefficient for solar admission, visible transmittance for daylight, air leakage for infiltration, and condensation resistance for interior surface temperature. Each one is certified for the entire assembled window, frame plus glass plus spacer. 5 metrics, each one measuring a specific window behavior. 5 NFRC metrics, each measuring a different aspect of window performance. U factor measures the rate of heat transfer through the window assembly in British thermal units per hour, per square foot, per degree. Lower is always better because it means less heat loss in winter and less heat gain in summer. The range runs from about 0.15 for a high-performance triple-glazed unit to about 1.2 for a single-pane window. Solar heat gain coefficient, called SHGC, measures the fraction of incident solar radiation that gets admitted through the window. And unlike U factor, the desired value depends on the climate. In a heating-dominated climate, you want higher SHGC to capture beneficial solar gain in winter. In a cooling-dominated climate, you want lower SHGC to keep the sun out. Visible transmittance, abbreviated VT, measures the fraction of visible light that gets through the window. Higher is generally better for daylighting because more daylight reaches the interior and reduces the electric lighting load. Air leakage measures the rate of unintended air infiltration through the window assembly, and lower is always better because infiltrating air carries unconditioned heat or cold into the space. And condensation resistance measures the window's ability to resist condensation on its interior surface, scored 0 to 100, with higher being better. Climate decides whether high or low SHGC is the right answer. 3 climate-based glazing strategies the exam tests directly. In a heating-dominated cold climate, The priority is minimizing heat loss with very low U factor below 0.3, while allowing solar gain with higher SHGC above 0.4, especially on south-facing glass that can deliver useful winter heat. The window does double duty as a passive solar collector in winter. In a cooling-dominated hot climate, the priority flips. Minimize solar gain with very low SHGC below 0.25, and keep U factor low to limit heat conduction through the assembly. Solar gain is the enemy here, not the friend. In a mixed climate, the design balances both. Moderate values for both metrics, often using spectrally selective low emissivity coatings that allow visible light through while blocking infrared. The light-to-solar gain ratio, called LSG, becomes important in cooling-dominated climates where you want daylight without the heat. Spectrally selective coatings push LSG well above 1, which is the high-performance target. Carry the 5 NFRC metrics and the 3 climate strategies into the moisture management section. 5 takeaways for window performance specification. There are 5 NFRC-rated metrics on every code-compliant window: U factor for heat transfer, solar heat gain coefficient for solar admission, visible transmittance for daylight, air leakage for infiltration, and condensation resistance for interior surface temperature. Heating-dominated cold climates want very low U factor, below 0.3, to minimize heat loss, combined with higher SHGC above 0.4 to capture beneficial winter solar gain, especially on south-facing glass. Cooling-dominated hot climates flip the priority. Very low SHGC below 0.25 to keep solar gain out, with low U factor to limit heat conduction. Spectrally selective low emissivity coatings push the light-to-solar gain ratio above 1 by allowing visible light through while blocking infrared radiation, which is the high-performance target for cooling-dominated daylighting. And always specify to NFRC certified whole window values rather than marketing center of glass numbers, because the marketing values are always better than the certified values, and using the wrong number gets the project redlined at Energy Code Review. Most architects can name an air barrier and a vapor retarder, and most architects cannot tell you which side of the wall the vapor retarder belongs on in a hot, humid climate. You should be able to answer that question without checking a reference. There are 3 moisture control layers in a properly designed wall. The air barrier prevents air leakage, the vapor retarder limits moisture vapor diffusion, and the water-resistive barrier drains liquid water that gets through the cladding. Each one handles a different moisture path, and missing any one of them lets moisture into the wall through the path that layer was supposed to cover. The vapor retarder placement is the exam trap. Wrong climate, wrong side, the wall traps moisture, mold grows inside the assembly, and the lawsuit that follows names the architect personally liable for the design defect. There is no variance, no waiver, and no professional liability defense for a vapor retarder on the wrong side. Get it right at design or pay for it at occupancy. 3 control layers, each placed at a specific point in the assembly. 3 moisture control layers, each placed at a specific point in the wall assembly. The air barrier prevents air leakage through the assembly and must be continuous across the entire enclosure, not just the wall, but every connection at the foundation, the floor slab, the roof deck, and every window and door opening. Air leakage carries far more moisture into a wall than vapor diffusion does, which is why air barriers have become the priority moisture control layer in modern construction. The vapor retarder limits the diffusion of moisture vapor through the wall and is placed on the warm side of the insulation, where the warm side varies by climate. Common materials include polyethylene sheet, craft paper, and vapor retarder paint. The water-resistive barrier sits behind the cladding and over the sheathing, and its job is to drain any liquid water that gets through the cladding so that water cannot accumulate against the structural sheathing. Common materials include building wrap like Tyvek, fluid-applied membranes, and traditional building felt. The air barrier and the water-resistive barrier are sometimes combined in a single product to simplify installation. The vapor retarder placement rule by climate is the exam trap. 3 climate zone rules for vapor retarder placement, and the exam tests this directly. In hot or warm climate zones 1 through 3, the cooling load dominates, and the wall is warmer outside than inside for most of the year. The vapor retarder goes on the exterior side or is omitted entirely. Placing it on the interior is a serious design defect because it traps moisture vapor inside the wall where the interior surface is cool from air conditioning. Moisture condenses behind the interior finish, mold grows, and the building sues the architect. In cold climate zones 5 through 8, the heating load dominates, and the wall is warmer inside than outside for most of the year. The vapor retarder goes on the interior side, the warm in winter side, to stop interior humidity from pushing vapor outward into the cold wall cavity, where it would condense on the sheathing. In mixed climate zone 4, the design has to handle both directions. The standard answer is a smart vapor retarder with variable permeance that adjusts to humidity conditions, or a case-by-case analysis that picks the location based on the dominant load. Thermal bridging compounds the moisture issue. Steel studs can drop wall R value by 40 to 60% because steel conducts heat much faster than wood or insulation, which is why continuous insulation outboard of the framing is required by ASHRAE 90.1 in most climate zones. Carry the 3 layers and the climate zone rule into the lead and energy code sections. 5 takeaways for moisture management and thermal bridging. There are 3 moisture control layers in a properly designed wall. The air barrier prevents air leakage, the vapor retarder limits moisture vapor diffusion, and the water-resistive barrier drains liquid water from behind the cladding. The air barrier matters more than the vapor retarder in modern construction because air leakage carries far more moisture into a wall than vapor diffusion does, which is why air barrier continuity has become the priority quality control item on every project. The vapor retarder goes on the warm side of insulation, but climate decides which side is warm. Interior for cold climate zones 5 through 8, exterior or omitted for hot climate zones 1 through 3. Cold climate zones 5 through 8 place the vapor retarder on the interior side because the heating load dominates and the wall is warmer inside than outside for most of the year. And putting the retarder on the wrong side traps moisture and grows mold. And continuous insulation outboard of the framing avoids the thermal bridging that steel studs create, which is exactly why ASHRAE 90.1 mandates continuous insulation in most climate zones for steel-framed walls. Most architects sell LEED to owners as marketing, and most architects fail to deliver the certification they promised because you cannot earn gold or platinum without an energy strategy that hurts. LEED version 4.1 for building design and construction allocates 110 total points across 8 major categories plus integrative process, and the math is not subtle. Energy and atmosphere alone is 33 points, which is more than any other category and almost a third of the total. Hit energy hard or never see platinum. The architect who promised a gold certification to win the project and delivered certified because the energy model came back weak is the architect who gets sued for breach of contract. The firm pays the difference on the project cost, and the case becomes the reason the firm's professional liability premium goes up next year. The certification levels are certified at 40 to 49 points, silver at 50 to 59, gold at 60 to 79, and platinum at 80 or more. 8 major LEED credit categories spread across the project life. 8 major LEED categories spread across the project's design and construction, plus integrative process at one point for early design analysis of energy and water systems before schematic locks decisions in. Location and transportation awards 16 points for site selection, transit access, and reduced automobile dependence. all of them decided at site selection rather than during design. Sustainable Sites awards 10 points for stormwater management, heat island reduction, and protected open space. Water Efficiency awards 11 points for indoor and outdoor water reduction below baseline, with a 20% indoor reduction required as a prerequisite to even qualify for certification. Energy and Atmosphere awards 33 points, the largest single category, for energy performance versus baseline, commissioning, on-site renewables, and refrigerant management. Materials and Resources awards 13 points for life cycle assessment, environmental product declarations, sourcing transparency, and construction waste reduction. Indoor Environmental Quality awards 16 points for indoor air quality, thermal comfort, daylighting, acoustic performance, and views. Innovation awards 6 points for strategies that exceed credit requirements or address issues not covered elsewhere. And Regional Priority awards 4 points for credits the USGBC has flagged as regionally important to the project's location. 4 certification levels turn point totals into formal recognition. 4 LEED certification levels turn the project's point total into a formal recognition that the owner can put on the building, on the marketing materials, and on the lease offering. Certified is the baseline level at 40 to 49 points, which represents a project that has implemented sustainable strategies, but at a modest level. Silver is at 50 to 59 points and signals a project that has made meaningful sustainability commitments across most categories. Gold is at 60 to 79 points and is the level most ambitious projects target. Gold is achievable with strong energy and atmosphere performance, combined with 2 or 3 other category wins. And Platinum is at 80 or more points, which requires exceptional performance across nearly every category and is the hardest level to reach because the jump from Gold to Platinum is the steepest. Most projects targeting LEED aim for Gold because it gives meaningful market differentiation without the cost premium that Platinum demands. The certification level the architect promises at the proposal stage is the level the firm has to deliver, or the firm gets sued for the difference between promise and delivery. Carry the 9 categories and the 4 levels into the Energy Code section that follows. 5 takeaways for LEED credit structure. There are 8 major LEED version 4.1 building design and construction credit categories, plus the integrative process credit, totaling 110 points, and the categories span the full range from site selection through indoor environmental quality at occupancy. Energy and Atmosphere alone is 33 points, the largest single category by a wide margin, which reflects the reality that energy efficiency has the largest environmental impact of any sustainable design decision the project will make. There are 4 certification levels: certified at 40 points minimum, silver at 50, gold at 60, and platinum at 80 or more. And the gap between gold and platinum is the hardest to close because platinum requires exceptional performance across nearly every category. Most projects targeting LEED aim for gold because it provides meaningful market differentiation, comfortable margin over silver, and avoids the cost premium that platinum demands on top of the design work. And the certification level promised at the proposal stage is the level the firm has to deliver at certification. Promise gold and deliver certified, and the firm gets sued for the difference, including the rent premium the owner expected to charge based on the marketing claim. Most architects treat the Energy Code as the engineer's compliance exercise, and most architects find out at permit review that you cannot ignore it. ASHRAE 90.1 and the IECC are mandatory minimums adopted by every state and most cities, and the project does not get a building permit until the Energy Code calculation passes. The architect who skipped the energy compliance review at design development is the architect whose permit gets denied. The project loses 6 weeks of schedule while the design team scrambles to substitute windows and add insulation. And the firm gets sued for the lost rent that follows. 4 compliance paths trade prescriptive simplicity for performance flexibility. The prescriptive path requires each component to meet its individual requirement with no trade-offs allowed. The trade-off path lets envelope components trade against each other. The energy cost budget path uses whole building simulation against a baseline, and the performance rating method in Appendix G is used for lead credit and beyond code design. Pick the wrong path and the project costs more than it had to. 4 compliance paths from least to most flexible. 4 ASHRAE 90.1 compliance paths, each one trading prescriptive simplicity for performance flexibility. The prescriptive path requires each component of the building, every insulation R value, every window U factor, every lighting power density, every HVAC efficiency rating, to meet its individual requirement with no trade-offs allowed between them. It is the simplest path to document and the least flexible to design. The trade-off path, sometimes called the envelope trade-off path, allows trading between envelope components using a tool like ComCheck or the Appendix C method. For example, better windows can offset weaker walls if the combined assembly meets the same overall energy target. Moderate flexibility, modest documentation burden. The energy cost budget path uses whole building energy cost simulation against an ASHRAE baseline building, and any combination of envelope, mechanical, and lighting that meets the total energy target qualifies. The flexibility is high, but the simulation is expensive. And the performance rating method in Appendix G is used primarily for lead energy and atmosphere credit and beyond code design work. It is more detailed than the energy cost budget path and provides the highest design flexibility, but the simulation effort is the largest. 5 regulated components define what the energy code actually covers. 5 building components regulated by ASHRAE 90.1, each one keyed to the project's climate zone. The envelope is regulated by minimum insulation R values for walls, roofs, and floors, plus maximum fenestration U factor and solar heat gain coefficient, and the numbers tighten as climate zones get colder. HVAC equipment is regulated by minimum coefficient of performance, energy efficiency ratio, and seasonal energy efficiency ratio for cooling equipment, plus required economizers above certain cooling capacities and required controls, including demand-controlled ventilation in specified space types. Lighting is regulated by lighting power density limits in watts per square foot, with separate caps for every space type under the space-by-space method or a single building-wide cap under the building area method. Surface water heating is regulated by minimum water heater efficiency and required pipe insulation on hot water lines above a threshold diameter. And electrical power is regulated by transformer efficiency, motor efficiency at the premium efficiency level for most motors above 1 horsepower, and voltage drop limits on long branch circuits. All 5 components scale their requirements with the climate zone, with the 8 ASHRAE climate zones ranging from Hot Zone 1 in southern Florida to Cold Zone 8 in northern Alaska. Carry the 4 compliance paths and 5 regulated components into the passive design section. 5 takeaways for energy code compliance. ASHRAE 90.1 and the IECC are mandatory minimums adopted by every state and most cities, and the project does not get a building permit until the energy code calculation passes. There are 4 compliance paths, from prescriptive at the least flexible end to performance rating method at the most flexible end, with trade-off and energy cost budget filling in between. Each one trades simulation effort for design flexibility. 5 components are regulated by the energy code: envelope, HVAC, lighting, service water heating, and electrical power. And each component has its own requirements keyed to the project's climate zone. There are 8 ASHRAE climate zones running from Hot Zone 1 in southern Florida to Cold Zone 8 in northern Alaska, with moisture designators A for moist, B for dry, and C for marine. And the requirements tighten as climate zones get colder. And picking the wrong compliance path costs more than the project had to spend, because a prescriptive path on a project that could have traded would force unnecessary upgrades, while a performance rating method on a simple project burns simulation budget for flexibility the project did not need. Most architects treat passive design as a sustainability checkbox, and most architects miss the chance to cut the mechanical load by 20 to 40% before the MEP engineer even sizes the equipment. You can build a building that needs half the air conditioning capacity if the passive strategies are sequenced correctly at schematic design. 6 passive strategies cover almost every climate: building orientation, thermal mass, natural ventilation, shading devices, earth sheltering, and cool roofs. And the order of operations matters. Orient the building first, then size and locate the glazing. Then add shading appropriate to each facade. The architect who designed the south facade as a glass curtain wall in Phoenix is the architect whose owner sues for the cooling cost overrun. The firm gets back-charged for the chiller upsize the design forced, and the building never reaches its energy target. South-facing overhangs work in temperate climates because the sun is high in summer when you want shade, and low in winter when you want solar gain to enter the building. 6 passive strategies, each matched to climate. 6 passive design strategies, each matched to a climate context. Building orientation with the long axis east to west maximizes south exposure for winter solar gain and minimizes east and west exposure where the low-angle morning and afternoon sun is hardest to shade. The strategy applies in all climates, but matters most in heating-dominated zones where winter solar gain is a useful free heat source. Thermal mass, heavy materials like concrete, masonry, or stone, absorbs heat during the day and releases it slowly at night, which works well in climates with large diurnal temperature swings like the desert Southwest, where daytime and nighttime temperatures differ by 20 degrees Fahrenheit or more. Natural ventilation uses operable windows, stack effect, and crossflow to move air without mechanical systems, which works in mild climates and swing seasons, but requires careful aperture sizing. Shading devices block unwanted solar gain on south and west exposures, overhangs on south, vertical fins on east and west, and work in cooling-dominated climates and any orientation where the sun is the enemy. Earth sheltering uses below-grade or bermed walls to reduce heat loss in winter and heat gain in summer, which works in extreme climates where the steady earth temperature beats the swing of surface temperature. And cool roofs use high reflectance and high emittance materials to reject solar radiation, which is required by IECC in cooling-dominated climate zones. 5 daylighting principles complete the passive design package. 5 daylighting design principles that complete the passive package. First, the effective daylight zone depth runs roughly 1.5 to 2.5 times the window head height into the room. A 10-foot head height gives you a useful daylight zone 15 to 25 feet deep, which sets the maximum perimeter office depth that can rely on side lighting alone. Second, side lighting from windows is effective to about 15 to 20 feet from the window wall, which is why deep open offices need supplementary top lighting. Third, top lighting through skylights, monitors, or clear stories serves deep floor plates that side lighting cannot reach, useful for sports facilities, factories, and any space too deep for windows alone. Fourth, light shelves are horizontal elements mounted at window head height that bounce daylight off the ceiling and deeper into the space while shading the lower glass and reducing glare at the work surface. And fifth, photoelectric dimming controls are required by ASHRAE 90.1 in primary daylit zones above prescribed thresholds. They dim or switch off electric lights when daylight is sufficient, which captures the energy savings that the daylight strategy was designed to deliver. LEED awards credits for daylighting 55% or 75% of regularly occupied spaces, depending on the target tier. Carry the 6 strategies and 5 daylighting principles into the water conservation section. 5 takeaways for passive design and daylighting. There are 6 passive design strategies: building orientation, thermal mass, natural ventilation, shading devices, earth sheltering, and cool roofs, and the order matters. Orient the building first, then size and locate glazing. Then add shading appropriate to each facade orientation. Then specify thermal mass where diurnal swings justify it. South-facing overhangs work in temperate climates because the summer sun is high and the overhang blocks it, while the winter sun is low and enters below the overhang to deliver beneficial solar gain. East and west exposures are the hardest to shade because the sun angle is low and a horizontal overhang cannot intercept the morning or afternoon sun. Vertical fins or external screens are the right answer for east and west facades. Daylight zone depth runs roughly 1.5 to 2.5 times the window head height into the room, which sets the maximum perimeter office depth that can rely on side lighting alone, with deeper floor plates needing top lighting or supplementary electric light. And photoelectric dimming controls are required by ASHRAE 90.1 in primary daylit zones above prescribed thresholds. They capture the energy savings that the daylight strategy was designed to deliver. Otherwise, the electric lights stay at full output regardless of daylight. Most architects treat water conservation as the plumbing engineer's checkbox at the end of design development, and you cannot afford that habit anymore. Water conservation is a prerequisite for LEED certification. 20% indoor water reduction below baseline is required just to qualify. No credit awarded for hitting it, just a gate the project has to clear to be considered. The architect who promised LEED on the project and missed the water prerequisite is the architect who delivers no certification at all. The firm gets sued for breach of the LEED contract clause, and the design fee absorbs the cost of swapping out fixtures during construction. 5 indoor fixture upgrades deliver 20 to 77% reduction on the major loads: water closets, urinals, lavatory faucets, shower heads, and kitchen faucets. And the WaterSense label drives most of the specification work. 5 outdoor strategies extend the savings: native landscaping, rainwater harvesting, gray water reuse, drip irrigation, and cooling tower water management. Add them together, and the building uses half the water of an equivalent baseline project. 5 indoor fixtures cover almost every code-driven water demand. 5 indoor fixtures and the efficient flow rates that drive the LEED water credit. Water closets baseline at 1.6 gallons per flush, the federal standard since the 1992 Energy Policy Act, and efficient water closets cut that to 1.28 gallons per flush, a 20% reduction. Dual flush models with 1.6 gallons for solids and 0.8 gallons for liquids can hit the same weighted average. Urinals baseline at 1 gallon per flush, and efficient models cut that to 0.5 gallons per flush, with waterless urinals dropping the number to 0, a 100% reduction on that fixture line. Public restroom lavatory faucets baseline at 2.2 gallons per minute, and efficient models cut that to 0.5 gallons per minute, a 77% reduction that is the easiest water credit available because the WaterSense aerator costs almost nothing. Private residence lavatories run higher at 1.5 gallons per minute to maintain comfort. Shower heads baseline at 2.5 gallons per minute, and efficient models run 1.5 to 2 gallons per minute, a 20 to 40% reduction. And kitchen faucets baseline at 2.2 gallons per minute, and efficient models run 1.5 to 1.8 gallons per minute. Together, low-flow fixtures are the easiest and most cost-effective path to LEED water efficiency credits because the marginal cost is small and the savings are immediate. 5 outdoor and process strategies extend the savings beyond fixtures. 5 outdoor and process water strategies that extend savings beyond indoor fixtures. Native and adapted landscaping uses plants that evolved with the local climate and rainfall pattern, which means irrigation is reduced or eliminated. Drought-tolerant native species can survive on natural rainfall in many climates. Rainwater harvesting captures roof runoff in cisterns and tanks for non-potable use, including irrigation and toilet flushing, and the captured water is relatively clean because it has not touched the ground or any contaminated surfaces. Gray water reuse takes wastewater from sinks, showers, lavatories, and clothes washers, relatively clean wastewater, and treats it for reuse in irrigation or toilet flushing, with code approval required in most jurisdictions. Do not confuse gray water with black water, which comes from toilets and kitchen sinks and requires full sewer treatment because of pathogen and food waste load. Drip irrigation delivers water directly to plant roots through a network of tubing and emitters, achieving roughly 90% or higher efficiency, compared to 50% for spray systems, where most of the water evaporates before it reaches the soil. And cooling tower management maximizes the cycles of concentration in the tower water before discharge, which reduces the makeup water demand on buildings where cooling tower water dominates the consumption profile. Together, these outdoor and process strategies layer on top of the indoor fixture savings and push the project well past the lead prerequisite. Carry the indoor and outdoor strategies forward as the closing piece of the building systems module. 5 takeaways for water conservation strategy. 5 indoor fixture upgrades cut water use by 20 to 77% on the major fixture loads: water closets, urinals, lavatory faucets, shower heads, and kitchen faucets. And the WaterSense label drives most of the specification work for compliant fixtures. LEED requires a 20% indoor water reduction below the 1992 baseline as a prerequisite for certification, which means projects that miss it deliver no certification at all, regardless of how many points they earn elsewhere. 5 outdoor and process strategies extend the savings beyond fixtures: native landscaping, rainwater harvesting, gray water reuse, drip irrigation, and cooling tower management, and they layer on top of the indoor savings to push the project past the prerequisite. Gray water and black water are not the same. Gray water from sinks, showers, lavatories, and clothes washers is relatively clean and reusable with treatment for irrigation or toilet flushing, while black water from toilets and kitchen sinks carries pathogen and food waste load that requires full sewer treatment. And drip irrigation reaches roughly 90% or higher efficiency by delivering water directly to plant roots, compared to roughly 50% for spray systems, where evaporation steals most of the water before it reaches the soil. If you treat building systems as a menu, where any decision can happen in any order, every project you run will be a coordination nightmare. They are not interchangeable. Each system solves a problem the others can't, and the sequence is fixed because every layer constrains the layers below it. Structure comes first because the grid sets the column spacing every other system has to route around. Foundation comes second because soil-bearing capacity and frost depth determine whether the structure can transfer load to the ground at all. Mechanical, plumbing, and electrical come third because their sizing depends on the building's program, footprint, and orientation. Envelope comes fourth because climate, fenestration, and assembly performance set the heating and cooling loads. And performance closes the chain as the overlay. ASHRAE 90.1 and the IECC set the code floor, while LEED layers credits for the reach. Walk the chain in order and downstream coordination is possible. Skip a step and every later decision compounds the original mistake. The first 2 layers of the chain, structure and foundation, set the grid every other system routes around, so they belong at the start of the conversation. 3 concepts fix the structure and foundation strand. The load path is the architect's mental model. Every gravity load runs from the roof, down through floors, into beams, into columns, into the foundation, and finally into the soil. And every lateral load runs through diaphragms into shear walls or braced frames or moment frames, back down to the foundation, then into the soil. Structural system selection follows from span, height, fire rating, and material economy. Steel for long spans and tall buildings, concrete for mass, fire resistance, and acoustic separation, wood for low-rise and residential, and masonry for shear and bearing wall construction. Foundation selection follows from the soils report. Shallow foundations like spread footings and mat slabs work when soil bearing capacity is adequate near the surface and frost depth is shallow, while deep foundations like piles or drilled piers are required when bearing soil is deep or settlement risk is high. The mechanical, plumbing, and electrical layer is next, sized by program and constrained by the structural grid that just got fixed. 3 concepts run the foundational MEP layer. The all-air versus air-water decision is the HVAC system type fork. VAV with reheat is the workhorse for office and institutional buildings because air handles the latent and sensible load at moderate efficiency, while chilled beams and underfloor air distribution are higher performance variants that decouple ventilation from sensible cooling and recover energy more aggressively. Plumbing load is calculated from fixture units, with each fixture assigned a unit value per the International Plumbing Code, and the cumulative fixture unit count drives supply pipe sizing, vent sizing, and waste main capacity through the building. And lighting power density is the energy code lever the architect controls earliest. ASHRAE 90.1 and the IECC cap allowable watts per square foot by space type, so the lighting design either meets the cap through fixture selection and layout or burns the project's energy budget before the envelope is even drawn. Envelope and performance close the chain. The envelope sets the load the mechanical system has to meet, and the energy code sets the floor the envelope has to clear. 3 concepts close the envelope and performance strand. Wall assembly performance turns on continuous insulation outboard of the structure. Interrupting insulation with framing members creates thermal bridges that short-circuit the wall's R value, and continuous insulation is the cleanest detail for hitting modern energy code targets. Window performance breaks into 3 metrics the architect specifies independently. U factor governs conduction losses in cold climates, solar heat gain coefficient governs cooling load in warm and mixed climates, and visible transmittance governs how much daylight the window delivers to the interior. And the 3 metrics often pull in different directions, so the architect chooses based on climate and orientation. And the performance overlay is 2-tiered. ASHRAE 90.1 and the IECC set the energy code floor every project has to meet, while LEED v4 layers optional credits for envelope, energy, water, materials, and indoor environmental quality on top of that floor for the projects pursuing certification. 4 takeaways close the foundational arc into the sequencing discipline the module is training. Carry away from this module the sequencing discipline itself, the chain run structure, foundation, mechanical, envelope, performance, in that order because each layer constrains the ones below it, and the architect who jumps ahead to envelope before the grid is settled pays for it in coordination conflicts during design development. The structure foundation pair fixes the constraints every other system has to route around, column grid and foundation type together. So spending time on the grid early is the cheapest schedule insurance the project will ever buy. The MEP sizing logic is program-driven rather than intuition-driven. Fixture units run plumbing, lighting power density runs the electrical envelope, and ventilation rates and zone-level cooling loads run HVAC. And your job is to communicate program clearly enough that the engineers can compute. And the performance overlay is 2-tiered. The energy code is the floor every project has to meet, and LEED is the reach the project pursues if certification is part of the goal. But the 2 cannot be conflated because code is mandatory and credits are optional. Hold the chain. The module's questions resolve themselves when the order is right.